Okay, can you see my screen?
Yes, perfect. You can start.
Okay. Hello, everyone. I am Jun Liu, a PhD student of Guijun Zhang Lab at Zhejiang University of Technology in China. It is my honor to report our group's progress in accuracy estimation of multimeric complex. Here are the two motivations of our work. The first is that the relationship of local residues to the overall structure contribute to better representation of protein model. The second is how to distinguish the intermonomer structure relationship of the complex and how to characterize the relationship between a residue of one monomer and the other monomers. Based on the above motivations, we first proposed a monomer USR to characterize the relationship between residues and the overall structure in monomer. For monomer structure, each residue is considered as a point. For each residue OI, we can select the farthest residue Fi from it and the farthest residue FFI from Fi. These three positions represent the center of residue OI and its extremes in the structure. The distance from each residue in the structure to these three residues constitute three distance distributions. The first three moments of each distribution are used to describe the mean, variance, and asymmetry of this distribution. So the relationship between each residue and the overall structure can be encoded by 9 distributors. Furthermore, we proposed a complex USR to characterize the relationship between a residue of one monomer and other monomers in complex. For complex structure, we convert it into a point set, and each point represents a residue. For each residue I in monomer A, we first determine the nearest residue R and the farthest residue M in monomer B, and then determine the farthest residue N from residue M. So for each residue of monomer A, we can determine a unique triangle in monomer B. Based on the above strategy, we simplify the model. Similar to the monomer USR, we can obtain the distance distribution of these four residues by calculating the distance from each residue of monomer B to them. And each distribution is represented by its first three moments. We further extract the triangular pyramid formed by these four residues. To describe it, the unit normal vector of the triangle, the distance of residue I to the triangle, the length of the sides of the triangle, and the angles between IN, IR, IM to the triangle are calculated. So the relationship between each residue of monomer A and the topology of monomer B can be encoded by 22 distributors. Based on the above two key features, we began to represent the protein structure. For monomer structure, we use model-dependent features, co-evolutionary and template features to represent it. For the complex structure, we only focus on the model itself and represent it from three layers. The first is overall complex layer, which treat the complex as one large monomer structure, and the residue order independent features, such as monomer USR, voxelization expression, residue distance and orientations, amino acid properties are extracted. The second is the intramonomer layer, including sequence embedding, secondary structure, Rosetta energy terms. The third is the intermonomer layer. The paired sequence attention is used to express the sequence layer relationships, and the complex USR is used to characterize the structure layer relationship. Based on the above ideas and our previous work, we developed a new pipeline termed DeepYMQA3 for complex accuracy estimation. For the input complex structure, it is represented by the features mentioned above. We designed two networks. The first is an enhanced residual network based on triangle update and axial attention to predict pure residue LDDT of the complex structure and the interface residue accuracy. The second is a graph neural network to predict overall photo accuracy. For monomers self-estimation, we use the same network to predict LDDT for each residue. To train DPMQ3, we have constructed a complex structure model dataset from PDB database, which includes about 7,600 proteins. Each protein contains about 100 models. In CASP15, DPMQ3 ranks first in interface residue accuracy estimation. However, it is not ideal in the evaluation of overall interface accuracy and overall folding accuracy. For Q-score, we use the mean of the LDDT of all interface residues to represent it instead of specially trained QS score or DocQ, so which leads to unsatisfactory performance. For overall photo score, we have two versions. The first is the average LDDT of all residues of the complex structure, and the second is predicted by the graph neural network. These two versions are complementary in different performance metrics. Next, I will analyze the performance of our method on several cases. The first case is H1134, which consists of two different monomers. The average Pearson correlation of DPMQ3 on our models is about 0.696. The average ASE is about 0.89, and the average AOC is about 0.898. Taking a predicted model as an example, it can be found that the correlation ASE and AOC of the predicted interface residue LDDT and the real value are very high, and the predicted accuracy is close to the real accuracy on most interface residues. The main reason is that the complex USR can capture the influence of all the monomers to the local residues of the current monomer, while monomer USR can characterize the relationship between local residues and the entire complex structure. Currently, a pure residue LDDT of the complex structure predicted by DPMQ3 is also very close to the real quality. The predicted LDDT can capture the trend of residue accuracy variation. We also analyze the performance on overall photo accuracy estimation. Compared with the top rank group, our estimation is slightly worse in terms of correlation, but the predicted score is closer to the real value. The second case is T1170, which consists of 6 identical chains. Taking a model as an example, it can be found that the correlation ASE and AOC between the predicted interface residue LDDT and the real value are also high, and the predicted accuracy is close to the real accuracy on most interface residue. Similarly, the predicted pure residue LDDT of the complex structure is also very close to the real quality, and it is easy to distinguish the high and low quality regions from the overall structure. DPMQ3 can accurately access the accuracy for both interface residues and the pure residue of the complex, mainly because we consider the overall structure when designing features instead of only focus on interface. Here shows the performance of global photo accuracy estimation of our group 282 on this target. It can be found that the predicted TM score is very close to the real TM score, and they have a strong correlation. The third case is T1173, which consists of 3 identical chains. The performance of DPMQ3 on this target is the best among our targets. The average Pearson correlation is about 0.86. Here shows an example for interface residue estimation. The predicted accuracy is close to the real value on most of the residues. Although there are obvious differences in the loop located in the center of the structure, but the trends in the variation of residue accuracy are close, or very close. The predicted PR residue LDT can also well reflect the trend of real accuracy. On target H1137, we have poor performance. This target has 10 chains and about 4,000 residues. Limited by our computational resource, we evaluated 3 chains each time. Our chains are traversed in turn at the sleep size of 1 chain, and then integrate them together as the final estimation. This may lose important intermonomer information and is the main cause for poor performance. Here we show 2 examples of interface accuracy estimation for 2 models. The left shows a good correlation between the predicted and the real accuracy, and the right shows a poor correlation. Although we have poor performance on interface residue evaluation due to the limitation of computational resource, it shows good performance when evaluating the global fault accuracy on this target using our graph neural network. We're employing a lightweight graph neural network architecture that enables it to evaluate the global accuracy of larger complex structures. There are 3 reasons why DPO-MQ is working. The first is the monomer USR and the complex USR. The second is enhanced attention-based network. And the third is more complete dataset. There are 2 aspects for improvement. The first is domain-based interaction studies for large complex structures limited by their computational resource. The second is co-evolution and remote template exploration. Here I need to thank my mentor, dear Guijun Zhang, and the members of our lab. Also, we will appreciate that the CASP organizer provides the opportunity to let us share the model accuracy estimation experience. Thank you. That's all.
Thank you.